Okay. Hello, people. The room is full, and I love seeing this. Uh, we are going to talk about bringing NPCs, MetaHuman NPCs, to UEFN and what we learned during this process. But first, let me introduce myself. My name is Bojan Brankov. I represent Trilateral team, uh, member of Epic Games in Novi Sad. This is how I look in real life. And together with me, my esteemed colleague Thales Sabina is going to present, and not to be mistaken with the famous Greek philosopher and mathematician, but he's equally good engineer. I'm an engine developer, but we both are engine developers, and we worked on MetaHuman Creator on my side and MetaHuman Animator by Thales' side, and now we did some things for UEFN as well. We are going first to go down the memory lane and see what we did in MetaHuman ecosystem, what we did so far, and go through 5 phases of optimization of MetaHumans to make them ready for UEFN. So without further ado, let's start with a brief recap of the MetaHuman ecosystem and the tools available for you to use on your projects. We are proud by the quality of MetaHumans and the photorealism we achieved, almost bridging this uncanny valley that people always complain for. And until today, there are literal millions of MetaHumans released into the wild by you, thanks to our tools that are available for free from the start. MetaHuman Creator, my first child when I joined Epic Games, is cloud-based application that allows you to create high-fidelity digital humans. Probably most of you used it. It's through an easy user interface that you can quickly and intuitively create a photorealistic digital humans that are fully rigged and ready to use. Nobody else can give you fully rigged characters that are completely available to animate. Through the power of MetaHuman Creator, you can make MetaHumans in minutes, starting from one of the presets that we made for you. Or you can make your own custom mesh and then customize it in our Creator app. There's a MetaHuman plugin for Unreal that includes Mesh to MetaHuman, and we talked a lot about it in the past 2 years. It's an exciting feature that enables you to turn custom mesh created by scanning, sculpting, or traditional modeling methods into a fully rigged MetaHuman. And after converting your mesh, you can further refine your character in MetaHuman Creator, so they're interconnected. But there is a special feature we haven't talked about a lot, or at all, I think. That's a template to MetaHuman. It's a hidden feature of MetaHuman Animator. So I imported a skeletal mesh that is modified in one of the DCCs. And then I used the feature that is in assets that is called create from conformed. And then this skeletal mesh is directly transformed and made available as a static mesh template in MetaHuman Identity, MetaHuman Animator. This template, then, you don't have to conform, you don't have to promote frames, you don't have to find landmarks. But because, and that's very important thing to say, it is on MetaHuman topology. And when I press mesh to MetaHuman, I will have it fully rigged and available in MetaHuman Creator in the same moment. This is real-time video. I recorded it to see how fast you can get MetaHuman like this, resembling human with the features that you cannot make in MetaHuman Creator, but you can if you export some of our presets or your MetaHuman, import it in your favorite DCC, edit this, and then use this template to MetaHuman feature that I just saw to create something like this. Of course, these MetaHuman species here are created by a talented character artist, Goran Mamic. So if there are artists in the audience, I want to point one thing: the industry still needs you. You will not be replaced. We provide tools so you can easily bring your creations to life and cut the time needed to reach your goals by tenfold. Also available in MetaHuman plugin is MetaHuman Animator. You can use even any of these creations that I showed you previously to animate them. But this feature set enables you to capture an actor's performance using an iPhone or stereo HMC, then translate that capture into high-fidelity facial animation on MetaHuman characters. Every subtle expression, look, and emotion is accurately captured and replicated on your digital human. And you can see that. You can try that by yourself in our booth in the mezzanine. You come and we can have a short 10-minute session showing exactly this, what you see in this slide. MetaHuman DNA is an integral part of MetaHuman functionality. These files are created with MetaHuman Creator, and they are downloaded with Quixel Bridge in UE5. DNA calibration is a set of libraries and tools used to inspect and modify MetaHuman's DNA, and they're bundled into a single package, and you can access them in GitHub repository. You can download them, use them for free, calibrate DNA, and then recreate them using our tools in, for example, Maya or any DCC you can use. And this year, MetaHumans came to UEFN, and their debut is showcased in spring on GDC. This is Talisman. This is Captain Roo from Talisman project, our internal project, to test MetaHumans and push the boundaries of environments of UEFN. This set a stage for the work we needed to accomplish to get assets small enough and performant enough to hit the specs of the UEFN that UEFN requires. To give us better understanding of the challenges we were facing, let's look at some of the requirements that UEFN enforces. UEFN enforces certain restrictions for a better user and player experience. And we were made no exception to this rule. There's currently a 2 gigabytes total of project upload size and a total download size of 400 megabytes for one UEFN island. And the average Unreal MetaHuman cooked size comes to about 800 megabytes. That's cooked MetaHuman. Unprocessed MetaHuman, raw MetaHuman is even 2 gigabytes. So cooked MetaHumans is 4 megabytes over the total allowed limit for one island. And that's for the whole game, for all the assets in the level and everything. Since we are going to be working with UEFN parameters, we knew we were going to have to get creative and come up with ways to pack as much as we could, but only bring what was absolutely necessary. We also knew we had to retain the high visual MetaHuman fidelity, because our users expect that. We ended up taking a hard look at every aspect of what made a MetaHuman and determined its impact on the overall outcome. Everything from textures, materials, grooms, and animation performance, and meshes, they all had to be scrutinized. After a lot of hard work and effort, we are really excited to show you the results that we were able to accomplish. Let's take a quick look at the final result using 2 of our presets. You can see a high fidelity level UEFN MetaHumans across multiple platforms. With your UEFN islands being able to be played on across all major consoles, we wanted to make sure every MetaHuman was looking their best, whatever console they're seen on. From high-end to handheld devices, you can expect good-looking results across the board. Going through this process of getting MetaHumans to UEFN led to many improvements in optimizations, actually. But the most important I want to iterate is that the underlying MetaHuman functionalities remain the same, and that's important because everything that I'm going to show you here applies to MetaHumans in UE. In order to maintain compatibility with the MetaHuman ecosystem, we needed to make sure that we reduce what we reduce wouldn't affect your ability to use those tools that I presented in previous slides. With that in mind, we knew we wanted to use existing meshes without changing any geometry, as well as maintain the current rigs and skeletal hierarchy, and that's mandatory. These 2 areas we knew we weren't going to change at all, as it would have adverse effect on your ability to use these tools. This also meant we didn't need to create a new set of assets to maintain. The UEFN MetaHumans derive all of their assets from their Unreal counterparts, just tweaked to meet the needs of UN specs. So let's dive in. And before I start, just I don't know if I said, but MetaHuman Animator is also available in UEFN, so you don't have to go to Unreal, animate, and then import that in UEFN. You can directly do everything in UEFN editor. First thing that we've done with our MetaHumans is the performance scalability through the reduction of amount of LODs. Let's take a look how the UEFN MetaHuman level of details compare to the Unreal MetaHuman LODs. As mentioned before, the UEFN LODs are derived from the original MetaHuman, but they are not one-on-one mapping. We can see based on the left-hand side that LOD 0 high quality UEFN character is using LOD 1 of UE MetaHuman face, but LOD 0 of UE MetaHuman body, and so on down the line. We chose these LODs because they have the highest performance and quality with the lowest amount of footprint size. In order to maintain the fidelity of the next seam, we chose the corresponding head and body LODs that assure these edges lined up and properly syncs with the LOD sync component. What is LOD sync component? I will mention it in some of the future slides. Let's compare how the different levels of the UEFN relate to each other. The high quality, we have 3 tiers of UEFN MetaHumans. High quality character has total of 4 LODs. Medium has 3, and the low one has 2 LODs. Nobody needs more than that. You don't need the MetaHuman LOD 0. That's too much details for a small game. We can see in the graph that the medium and low quality versions are simply just stripped down versions of the high quality level. I want to point out here that you don't have to use every asset that comes with the MetaHuman downloaded. You're free to use and modify it, but it makes sense to your needs. If you're making small games, you definitely don't need all of it. Now I'd like to take a minute and talk about this LODC component that I mentioned. The MetaHuman blueprint brings together all of the different components to make a MetaHuman visual representation. Not all of the skeletal assets have the same number of mesh LODs. LODC component manages and synchronizes LODs across different MetaHuman component sizes, so they switch at the same time rather than individually and based on their own screen size, like normal as LOD do. This maintains the visual quality and consistency of all components, even when they don't share the same number of LODs. For example, the face as well as the grooms use 8 individual LODs, while the rest of the body use 4 LODs. For every 2 LOD changes that happen and face and groom components, only 1 LOD change happens for the rest. The LODC component controls this behavior. When adding your own custom assets in the blueprint, you'll need to update the LODSync component with your asset and configure how you want its LODs to sync with the rest of the MetaHuman. There are 3 attributes I want to call out. The first being the forced LOD attribute. This is the attribute that will force your whole character to a specific LOD, with -1 being the default and will let the system do the driving. However, if there is a specific LOD that you want to that you would like to see or debug, then you can specify a value and see the result in the blueprint viewport as well as in the editor. We use this quite often to visualize specific LODs and make sure the components are syncing as expected. So this is mostly used for debugging purposes, but the next attribute is the components to sync. Remember this one because this section determines which components are included and which components are actually driving the others. You can see that the body and face components are set to drive the other components. This means that whatever LOD body and face are using, the rest will use the corresponding LOD, even if their individual settings are different. Here, you would add any custom components and set its sync behavior. For example, if you added Chaos Cloth component to your blueprint, you would add it and likely set it as passive to sync with the body. Body does the driving for the cape. The third attribute is the custom LOD mapping. This is where you control how the LODs map to each other. Since the face has 8 total LODs and the body has only 4, the body component is being mapped with 2:1 ratio. The same with the other components. If I added a cloth asset, like I mentioned, and this mesh has only 4 LODs, I would add that component into this section and use the same 2-to-1 mapping. One last thing to note is that the driving skeletal mesh component gets its screen size setting from the skeletal mesh asset itself. This image is from the body scale mesh asset. The screen size setting for LOD0 is set to 1.2. This setting will determine when the LODs change and drive the rest of the components in the LOD sync. In this image, the screen size attribute is grayed out. That's because the MetaHumans we use, they share a data asset called LOD settings across all MetaHumans body types. You can open the MetaHuman LOD settings data asset and change the values there, which will update any asset using this data, or you can clear the LOD settings and have access to the individual assets. Now, I will let my colleague, Thales, talk about things he done to the textures and the rest. Thank you.
Hello, everyone. My name is Thales Sabino. I'm a senior software engineer here at Epic Games, and I worked on bringing MetaHumans to UEFN. So now let's talk about the process of baking textures for size reduction. Like Boyan mentioned, at almost double the limit for the UEFN island, it is clear that we wouldn't be able to bring a single MetaHuman to UEFN without massively reducing asset sizes. Textures account for 90% of a MetaHuman. 59% are textures that are used in the face materials alone. One of the reasons behind these numbers is that MetaHumans ship with 6 8K normal maps using the face materials alone, from which 3 are not the normal maps used for the dynamic wrinkles in the forehead. The cook size of these textures average at 30 megabytes, and this is only for normal maps. Enabling lossy compression is an easy way to reduce texture sizes. Even the lowest level of lossy compression can massively reduce the overall footprint of textures in your project. Let's take a look at the cooked asset sizes for a MetaHuman after enabling UDO lossy compression. From 782 to 404 megabytes, that's a 48% reduction in the overall size of a cooked MetaHuman. This is not bad for a single change in the texture assets, but we are still slightly over the UEFN island limit of 400 megabytes. And we are talking about a single MetaHuman here. Before jumping into the nitty-gritty of baking textures, let's look at some of the tools available for you to profile assets in your project. Available in UE through the right-click context menu in any asset, the size map is an interactive map showing the approximate size of an asset and everything it references. This is a good way to verify how much will be loaded when an asset is used in a level. Asset sizes are displayed from the largest to the smaller in the tool and allows you to zoom in and out to inspect further into the dependencies of your assets. The project size tool is available in UEFN and allows you to inspect how much each asset is contributing to the download size of an island. It allows grouping by asset type and gives you area of focus for optimizations. The statistics tool is available in both UE and UEFN and can be used to quickly list all assets in your project and compare their stats. The tool allows you to see primitive, texture, and shader stats in a tabular panel that allows sorting and filtering. Use this to quickly find which assets you need to optimize for your project. Available in UE, the Asset Audit tool allows viewing detailed information about assets. By enabling the write-back metadata to asset registry in the project settings, after cooking your project, you can see the staged compressed column, which shows you the cooked size for assets in your project, so you can decide which ones to target in order to reduce the overall footprint of the project. From the previous slides, it became clear that the texture should be the first focal point on reducing the size of MetaHumans for them to fit into the budget of UEFN islands, in a way to leave plenty of space for all the other assets that make a UEFN experience. So let's take a deep dive into the techniques we use to reduce the size of textures used by MetaHuman materials. If you watched the GDC talk, Achieving Realistic Visual Styles in UEFN, you may be familiar with this slide. If not, I highly recommend that you do, as we show not only what was done with MetaHumans, but also with the Talisman environment, and there are amazing tips and tricks for you to apply in your own projects. This diagram shows at a very high level the steps a MetaHuman take when you click on the download button in Quixel Bridge, or in Unreal, or the MetaHuman importer in UEFN. As you can see, In the path to UEFN, there is an extra step called pre-processing. I want to take this opportunity to talk more in detail about this step and what we did to get the average MetaHuman cooked at under 60 megabytes, and show you some of the techniques you can use to optimize assets in your project. The MetaHuman exporter is implemented as a MetaHuman creator commandlet. It takes all parameters you specify in MetaHuman creator and generates all the assets that make a MetaHuman that you can download. Setting up a commandlet in Unreal is really simple. All you have to do is create a class that inherits from uCommandlet and override its main function. The class is automatically registered in Unreal and is recognized when you run Unreal in the command line with the parameter run. In this example, I have a class conveniently named uMetaHumanExporterCommandlet that runs when you click on the download button in Quixel Bridge. And as you can see, the editor will add the u prefix and the commandlet suffix, so you don't need to type the whole name in the command line. The base commandlet class also provides you with a convenient way to parse the command line arguments using the parse command line function. In order to reduce the material complexity, we opt to use a set of 3 base materials. One material for eyes, one for skin, which includes the teeth, tongue, and body, and one for the fabric of the different clothing items. These materials are designed to produce a result that is very similar, if not identical, to the original skin materials of a MetaHuman. The difference is that by using baked textures, we are able to considerably reduce the complexity of these materials while maintaining the fidelity they provide. Let's take a closer look at the process of baking textures needed for this skin material. The original MetaHuman materials were designed to provide high-fidelity skin, eyes, teeth, and fabric, both up close and at a distance. To cover these use cases, these materials often end up containing complex pieces of shaded logic to allow them to be customized for different use cases. One such example is the use of makeup. The MetaHuman creator allows the appearance of a MetaHuman face to be customized by applying makeup to it. The skin material must account for this and provide all the necessary parameters. This includes the color, intensity, roughness, and the mask to where each piece should be applied in the MetaHuman face. Writing the baking process as an editor utility blueprint allowed our look dev artists to craft the baking process without the need for much engineering support. After the blueprint was complete, it was a matter of integrating it in the MetaHuman exporter commandlet to be invoked at the appropriate time. The process starts by producing a full MetaHuman that you would expect for a web project. It then evokes the baking script that I'm showing here, the baking script editor utility blueprint, to create the baked materials and textures. The first step is to get a reference to the original MetaHuman face material. From this material, we create a material instance dynamic that is designed to render exactly what the original material would, but instead of rendering to the screen, it writes the result to its emissive output. Note the call to copy material instance parameters. This node copies all parameters from the source material to the target material. This ensures that the baking material will have all its parameters set to what was configured for the MetaHuman. When drawing this material to a texture, we will get each texture as if the original material was used. The baking material is a version of the full skin material, but modified so that it can selectively write to its emissive output. We use a material function that is able to select which value to pipe to the emissive output based on the values of parameters set in the material. As an example, to bake the base color, we set the bake normal and bake specular parameters to 0, and then the series of lerps in the material will select the appropriate output to be rendered to a render target. The last step is to convert the render target into a texture. The resolution of the texture will be determined by the resolution of the render target, and that can be changed at runtime. This is how we control the resolution for textures for each of the face slots. Texture packing allows you to store multiple channels of data into a single texture. The final material can extract the relevant information from a single texture, thus saving a ton of space. Here you can see a very simple texture packer editor utility blueprint that I did as an example for this talk. On the left, where we have a material with 3 texture parameters. The material reads the art channel of each texture, packs them into a vector, and forwards them into the emissive output color of the material. The editor utility blueprints creates a material instance dynamic using this as the base material, sets the three texture parameters, and calls draw material to render target, and then convert render target to texture to update the final texture. All done in editor. Of course, this is an overly simplified version of a texture packer. Everything is using hard code references, but the basic idea behind baking textures for MetaHumans is this. Reducing the number of textures through baking and switching to a compact texture layout where possible already gave us great improvements regarding the overall cooked size of a MetaHuman. In this example, you can see that a high-quality version of Hudson in UEFN is using 92 megabytes. This is a great improvement, but we can do much better. We can clearly see that the Groom geometry now accounts for half of the size of this MetaHuman. So let's take a look at what we did to further reduce this number and get MetaHumans to a more manageable size. Just before moving forward, I just want to mention a new plugin that was added in 5.4 called Texture Graph. Texture Graph provides a node-based interface for you to create and edit texture assets directly in Editor. It allows you to combine blueprints, materials, and material functions to unlock unique workflows only possible within Unreal Engine. Texture Graph is currently experimental, but is definitely worth checking out. Now that you covered the process of baking textures, the next step is to optimize the next step to optimize MetaHumans for UEFN is to reduce the size of the Groom geometry, as it now accounts for roughly 50% of the MetaHuman. In this section, we are going to take a look at what we've done. We're going to take a look at how we've done it and what you can do to reduce the size of Grooms in your own projects. Grooms are an integral part of MetaHumans, but the strand-based rendering can be quite expensive, so we felt there could be a lot of potential savings to be found there. In Engine, Grooms provide a control to decimate strands and control vertices, which has a direct impact in the cooked size of a Groom asset. For UEFN, we try to pick numbers to achieve a good balance between quality and performance. The Groom asset editor provides several controls to change geometry and the appearance of your Grooms. The amount of Groom geometry you get after cooking the asset is determined by the curve and vertex decimation factors that can be found in the Interpolation tab of the Groom asset editor. A value of 0 means no strands or vertices, and a value of 1 means all strands and vertices. The actual number of strands and control points can be seen on the summary at the top of the Interpolation tab, and by changing the decimation factors, you can see how many strands and vertices you'll be left with. Selecting the right values for vertex and decimation and curve decimation can greatly impact the cook size of your Groom asset. In the case of Taro, if not decimating any data, his head alone would take 20 out of the 400 megabytes upper limit of UEFN islands. Moreover, rendering performance tends to decrease the more strands and control points you have in a Groom, so it's important to carefully consider both these values for your Grooms. Note that decimating vertices and curves doesn't affect the upload size for assets, since the actual reduction will be done at cook time. Another factor to consider is, of course, the looks of your character. You can use these properties to easily change the appearance of your character as demonstrated in these slides. The number you see in the bottom of each version is its cooked size. Horizontally, it's a variation of the curve decimation factor, and vertically is a variation of the vertex decimation factor. Strands can be further customized in the Strands tab. Changing width, root scale, and tip scale can be used to compensate for a reduced number of strands, as it helps to fill in the gaps. Here's an example where I selected very aggressive decimation factors. You can see that Taro's hair in this case goes really thin, but on the other hand, the cooked asset size goes to only 2.9 megabytes. One thing I can do in this case is increase its hair width to compensate for the lack of strands and get a more appealing visual. Let's see some examples. 0.02, 0.03, 0.04. So another time, 0.03, 0.02, and this is 0.01. At 0.04 centimeters, you get a very similar visual, even compared to its full Groom. It's clearly not the same, as more geometry means more fidelity, but at a distance, it's really hard to tell. It's not a bad trade-off for an almost 10x reduction in its cooked size. Let's take a final look at the asset size breakdown for Hudson after we applied decimation factors to its Groom. As you can see, the high-quality version of Hudson cooks down to only 64 megabytes now. One thing to note is that the Groom geometry still dominates at 35% of the whole MetaHuman, but Hudson's hair is one of the most complex hairstyles we currently have in MetaHumans. Now that we looked extensively at optimizations done to MetaHuman assets in terms of size, let's switch gears and talk about the MetaHuman component. The MetaHuman component is a new feature that was added to UEFN to allow MetaHumans to work and perform across all UEFN platforms. The MetaHuman component comes with all UEFN MetaHumans, and on the front end, it acts as a control center for the MetaHuman. It allows you to configure several performance scalability settings, such as the load thresholds on the body and the neck correctives for the physics simulations and clothing parts. Behind the scenes, the MetaHuman component is responsible for slotting the control rig and physics assets you set in the details panel to the correct animation blueprints that drive the animations of the MetaHuman. By breaking down the animation compute distribution, we were able to get a better idea of what areas were taking up the most compute time, and where we should start looking to improve. We noticed that the post-process animation blueprints was using a lot of compute time and realized we didn't have many options to tune in that area. We then created the UEFN MetaHuman component that allows you to scale your MetaHuman animation blueprint from a fully enabled character down to only running the skeletal mesh. Depending on your character, you can expect about a 20% faster difference between a fully enabled and a fully optimized MetaHuman. When profiling the animation blueprints, we discovered that the post drivers, rig logic, control rig, rigid bodies, and the IK fix-up can be quite expensive, depending on the complexity. We utilize all of these features in both the head and the body post-process animation blueprints. In order to help combat the performance cost of these nodes in Unreal, we added a load threshold attribute to all of these heavy compute nodes. By setting a load value, the graph will stop evaluating at that specific node after the load number is reached. Since the animation blueprints are not available in UEFN, the MetaHuman component will set these values in the MetaHuman for you. But in UE, you have the option to tweak these values yourself. To further optimize animation, there is now a post-process animation blueprint threshold on the skeletal mesh asset. This threshold will bypass the animation blueprint altogether and not process the graph at all. The main trade-off here will be the quality of the formations in the post-process animation blueprint, particularly the corrective poses for the body, as well as anything else you might have in the post-process graph that won't be evaluated. Use this to optimize the project when a MetaHuman won't be seen up close or won't have any facial animation applied to it. We did find that the neck correctives in the face post-process animation blueprint can provide a pretty big performance win without losing a lot of deformation quality. These correctives are used to fix the shape of the neck, especially at more extreme poses. You can set the load threshold to a higher load or simply disable them. The trade-off here is that the neck shape won't be as nice in certain poses. You can find all of the optimization settings for the neck in Rig Logic in the Anim Preview Editor window. We covered a lot of information today, so let's touch on some highlights to wrap things up. When creating more performant MetaHumans, we looked at 4 areas: the number of loads used, animation performance, Groom optimizations, as well as materials and texture savings. The MetaHuman component can be used as a control center to selectively enable MetaHuman features. Use the profiling tools to help you better understand what's expensive and where to start optimizing. With that, I'd like to say thank you all for joining us today. I hope you find this information useful, and I would like to invite Boyan back to the stage so we can take some questions. And if you don't have time to ask questions here, we are going to be at the MetaHuman booth for the rest of the day. Thank you.